This video introduces sampling and sampling distributions, which play a key role in inferential statistics. As a warning, sampling distributions are abstract and theoretical, and therefore the topic is arguably one of the most difficult in statistics. Let's begin with the sampling part. Surveys offer a way to tap into people's opinions. I'm sure you've seen survey results such as these. These surveys all attempt to say something about attitudes of a population as estimated from samples drawn from that population. To what extent can we rely on sample results to reflect the attitudes of an entire population? In this Nielsen survey, for example, how sure can we be that 14% of all households had over-the-air TV? The answer depends, at least in part, on both the size of the sample and how that sample was selected. Inferential statistics is a process of generalizing to a population from sample results. In order to have confidence in this generalization, the sample must be an accurate reflection of the population. In random sampling, every member of the population has a known, non-zero probability of being selected into the sample. Random sampling does not guarantee that the sample is representative of the population, but it ensures that any differences are due to chance fluctuations rather than systematic bias. Random sampling is not always possible. For everyone to have a chance to be selected, the population must be finite and listable. Let's say our population of interest is all 3-year-olds who were born prematurely, or all adults with Graves' disease. These are very large populations. Where would we find a list of all such individuals? For the 3-year-olds, by the time we assemble such a list, our population would be well over 3 years old. For adults with Graves' disease, we can't locate those who have not yet been diagnosed. They would not be on any list, and therefore, even though they are members of this population, they could not be included in the sample. So while random sampling is the gold standard for subject selection, we often rely on samples of convenience. For example, we work in a school system or a healthcare setting and have access to their records. Convenience sampling has the potential to introduce bias, systematic sources of error in estimating population characteristics, and may limit generalizability of results. However, no matter how the sample is selected, it should represent the population in the characteristics of interest. Because it is important that our sample represent the population to which we plan to infer our results, random sampling is an assumption of statistical tests. You may not always be able to draw a random sample, but you must consider whether the sample you draw is a fair one, that it represents the population. This is a research design issue, but it affects the interpretation of statistical results, so you should think very carefully about sampling when designing your study. Now let's look at sampling distributions. X bar is a sample statistic. It is also a random variable. It can take on more than one value, and we don't know what value it will take until we collect our data. Random variables have probability distributions. Therefore, statistics have probability distributions, which are called sampling distributions. A sampling distribution is a probability distribution for a statistic. Let's look at an example for binomial data. Y is the number of successes, and with large samples, we convert Y to a proportion, which we call p hat. The sample proportion of failures is called q hat. The hat, or circumflex, indicates an estimate of a population value. P hat is a sample statistic, so it has a probability distribution. This is the probability distribution of Y for the coin flip example, but instead of plotting values for Y, we plot values for P hat. This is the sampling distribution of P hat. The focus of all inferential statistics is on sampling distributions. When we do research, we have only one value for the sample statistic, but we compare it to a distribution of all possible values for that statistic. Sampling distributions are sample size specific. As sample size increases, the sampling distribution of p hat takes on more values, and starts to resemble the normal distribution. If the sample is large enough, we can use the normal distribution to determine probabilities. The rule of thumb to determine whether a sample is large enough is that n times p hat and n times q hat must both be at least 5. Suppose we had a sample proportion of 0.25. This is what n times p hat would be for 3 different sample sizes. The normal distribution could be used with sample sizes of 20 or 30, but not with a sample size of 10. I only need to test the smaller value. If this meets the rule, the larger value will also. When p hat is 0.1, we can see that not even a sample size of 30 is adequate. In general, the further away p hat is from 0.5, the larger the necessary sample size. When p hat is exactly 0.5, even a sample size of 10 would meet the rule. The parameters of the sampling distribution of p hat are its mean and standard deviation. The mean is equal to p, the population proportion of successes. The standard deviation of a sampling distribution is called a standard error. For the sampling distribution of p hat, it is equal to the square root of p times q over n. To summarize, a sampling distribution is a probability distribution for a sample statistic and represents all possible values for the statistic. Knowing the mean and standard deviation of the sampling distribution allows us to determine probabilities, which is what inferential statistics is all about.